Thanks for the introduction. Without further ado, let's start. So today I'm talking about one application of Spark at Adobe, and we are looking here at targeting in digital marketing. So give me a website and some free or reserved space on your website. You want to place some content on this website that is optimized or tailored to the visitor of the web page. The goal is to maximize a marketing goal, which might be maximizing revenue or the conversions or the number of customers, clicks, or maybe some more esoteric features or marketing goals such as experience. We have a set of actions that is a set of different content, advertisement, offers, and the like that we can expose to a visitor. We represent the visitor by numeric and nominal values in a vector. And so we are representing the customers or visitors at that point under contextual features, behavioral features, and experiential features. So contextual might be the time of the day or the day of the week, the geolocation. Behavioral features might be the time to the last visit, and experiential features are, for example, the customer has already seen action A1 and action A2 and so on. So what we are looking for here is a policy. A policy is basically a mapping from our state space to our action space. And we are looking for a policy that is optimizing, of course, our marketing goal. And that means that for each state we have, our policy selects the right action or the most promising action in that case. So in the following example, I'm just considering the marketing goal optimizing the conversion rates of visitors. That means we want to convert a visitor to a buying customer. And basically all the targeting models that exist right now have some notion of similarity, and they have either implicitly or explicitly a kind of segmentation of the users. And for each segment, they estimate the probability that this segment is converting. This is illustrated here in this step. And once we have this conversion rates for each segment and for each action, if a new visitor comes in the system, then we can select the closest segment of visitors. And then we can compare the conversion rates of these segments, and we pick the action with the highest conversion rate. So that's what our policy is doing. In order to train these policies, we, of course, need some training data. And when collecting the training data, we are running into some problems. So the big question is, when do we decide if a visitor is converting or not? So ideally, we are looking at the lifetime of a product or of a customer. That could be a product cycle or a season, whatever fits the product in this case best. And so just think, for example, you want to sell a phone. Then you're not interested in selling the phone right now, or you don't care if you sell the phone this week or today or in 1 month or whatever. At least as long as the price doesn't go down of the phone, you don't care when you sell the phone. But you want to sell the phone before you introduce the next phone. So in that case would be product cycle, very interesting. But the problem is you cannot wait until the product cycle is over to decide if a customer converted when seeing, or if your action that you selected was helpful that your customer converted after the product cycle. Because if you do so, then you know basically everything, but you cannot apply your data. So there's an unrealistic turnaround time. The other extreme is recording every page visit. So the customer comes in or visitor comes in, then the customer sees a web page, and then you decide if the customer converted or not. This would result in a very myopic optimization in the end if we apply the state-of-the-art targeting models. That is maybe comparable to, let's say you have some policy which is trying to sell you a car, and then you have this policy which is saying, okay, you can take this car for this special offer, but that's only valid for today. And compared to the other policy, which is saying, like, you can come back every time, I will give you the best offer. So the first strategy is very aggressive, and that's what we call myopic here in that case. And we are trying to avoid this in the end. So what's currently done by many solutions in the industry is a kind of compromise where we are logging the data by session. So once the customer leaves your website, then we decide if the customer converted or not. The big question now is, can we reach the goal of optimizing for a lifetime value of a visitor with taking the data from a very fine granular level? And yes, that's possible. Therefore, we can employ reinforcement learning algorithms. And the basic idea is we are looking at trajectories of the customer on your website. So a group of customers is starting on a specific page of your website, and then the group of customers can transfer to other pages on your site. And then in another step, the people can, again, go to another site. So there's this idea of transitions going on your website. So you have a current state, then you apply an action, and then you go to a follow state. And depending on what action you select, there are specific probabilities that you end up in a specific web page. And so and also we have the conversion probabilities for each action or for each transition. And we can combine this with reinforcement learning in order to estimate the lifetime value of a product. But first of all, I'd like to mention how we are using Spark for estimating the transition probabilities. So how many people of you have used Hadoop or Spark? So once you've done this, then you probably start with a word count example, where you basically just count or aggregate the word counts over a huge collection of documents. And here the basic idea is very similar. Instead of counting words, we are counting transitions. So in the first step, we are using here a specific data structure, which is using a triple as a key. We have the current state, then an action, and then a following state. And the value is R and C. So R is 1 if the visitor converges during this transition, and C is always 1. It's just a counter. So in the second step, we are adding up the conversions and counts for each transition. That means we are using reduce by key. That is, we are collecting all the entries with the same key, that are all the transitions, and then we are building the sum of all the conversions, and we also sum up the counter. In the third step, we are basically normalizing the conversions and counts. Therefore, we use group by and map. We use group by in order to collect all the transitions that have the same current state and then the same action. And for estimating the transition probability for SAS prime, we basically take the sum, which we already have, of the counts, and then we divide this number by the number of transitions, the number of S and A. And we are basically doing the same trick for estimating the conversion rate and call this R like reward. In the end, we store the results of this in a specific data structure, which I explain on the next picture here. So we are basically using, again, as keys, the current state and the action we like to employ. And as values, we take the targeting values, the values are basically hash maps. And in each hash map, we use, again, the follow state as a key, and the value is the transition probability and the conversion probability. And the nice thing, if we take this data structure, is that we have all this stuff here, all the ingredients for a key and the corresponding transitions are collected on one node in our Spark cluster. And This is very nice if we look at the policy iteration algorithm, where we trying to combine the transition probabilities and the conversion probabilities in order to estimate the lifetime value. So this algorithm, I give a rough explanation, has two steps. So we have policy evaluation and policy improvement. In the policy evaluation step, we are basically taking a policy that we already have. So again, a policy is a map from a state to an action. And for this policy, we want to find out what is the value of a state if we employ this policy. So the basic idea is that we take the conversion rate and weight this conversion rate by the probability that we are actually going to the corresponding follow state. And then we add up the value from the follow state with a discount factor. So the nice thing here is that because of our data structure, we already partitioned the data in a way that we find all the ingredients for cooking this sum here on one node. And as we have to do this for each state in our state space, we can easily parallelize this. The same happens here in policy improvement. Here's the basic idea that we again do basically the same computation, but the goal is to improve our policy that we have by selecting the most promising actions. So we did some experiments comparing Spark versus Hadoop, and we basically came up with 3 different data sets. And the outcomes were, for example, that we can run the computation for the transition model 7 times faster when we are using a 20-instance cluster on AWS compared to using only 1 instance. And also, Spark is outperforming Hadoop in almost all cases and can also run up to 71% faster. And another observation is that if we use a very small data set, then it doesn't really matter if we use a 10-instance cluster or a 20-instance cluster. So let's look a little bit more into detail for the second data set. This data set is from Adobe Test and Target. I don't tell you what company we are supporting here, but we have 10 gigabytes of data. We are using, in that case, 450 features. We have about 4 million states, and the transition model results into about 7 gigabyte space. But if we represent the states not by the vectors I described, but by the hash values of this vector, that means 1 hash value per vector, then the transition model is about 234 megabytes big. So taking the same data set and then running the experiments on different sized clusters. So we have also different frameworks here, like Spark and Hadoop. Then we can see that the execution time, which is 40 minutes when running with Spark on a cluster with 1 master and 1 slave, can be reduced to 5 minutes if we go to a 20 minutes cluster. And also, if we represent the states not by the vectors, but by the hash values of the vectors, then we can reduce the time further to 3 minutes. And compared to Hadoop, this is 3 minutes against 8 minutes Hadoop runtime. So for the policy iteration algorithm, I selected a smaller data set because there we have a quadratic runtime or complexity in this problem. And that's also why we are not using this in production. But it's still a nice example here. So we get, in policy iteration, 7.5 seconds per iteration on a single machine. Then we can shrink the runtime to 1.7 seconds if we use a cluster with 10 instances, and we can further reduce it to 1.25 seconds if we use a 20-instance cluster. So last comment, we are looking for interns. If you have some background in machine learning, data mining, distributed systems, streaming applications, and then OR, so you don't have to be able to do all this stuff, or information visualization, then please let me know. Come to me after the talk or just send me an email. Thank you for your attention.
Thanks, Nedim. All right, a couple questions.
So I noticed in your computation of the transition probabilities and the convergence probabilities, you didn't smooth them. Is there a reason behind that? And if you do smooth them, how do you go ahead and do that?
What was the problem with the transition?
You didn't smooth them in that update rule. And then if you do that, how do you do it in this parallel environment?
Yeah, in fact, we are not using this approach in production. That's just for trying to figure out how we can leverage Spark. And I wouldn't recommend to use this in any targeting model, because you don't have this abstraction model, and you still have to map your incoming visitor to the corresponding state in order to use the computed transition probability. And that's not really practical at that time. Okay.
All right. Actually, that's all the time we have for questions. So let's thank our speaker again from Adobe.